All right. Hey, everyone. So this is the third part lesson dealing with differential equations. In the first one, we were using approximation strategies called a linear approximation to approximate values. So we were creating a tangent line and saying, okay, if we just kind of use the tangent line as a rough guess of what the original function is doing, we can approximate what the real function is doing at different values. That was the first thing. Second thing was creating a slope field and saying, okay, based on how the slope is working, we can kind of piece together what the original function is doing. There are lots of other ways to approximate what's happening in differential equations, but none of them are as good as if you can find the actual function. So if you can find the original function, then you don't even have to approximate. You have the original function. And that's one of the things we're doing today. It's called finding the particular solution. In other words, it just means find the original function. Find the original function. That's the goal. I'm going to show you the process. Process, not too bad. If you're good at it, it's not bad. If you struggle, it takes a lot of practice. Okay, it's one of those things that gets messed up a lot. So my goal is to make you practice this a ton with me. So I'm going to go through the process with you using that one that we've now dealt with a couple times. The differential equation that looks like this. Don't worry, this one's a little weird because there's no x's in it. When you have a combination of x and y, it's a little bit follows the same pattern. But this is a good one to recognize because this actually does pop up a lot. Problems where you don't have the x. So our goal is to find the original function. What you need to do this is you need to get all of the y terms on the left. So y's on the left. X is on the right. What do I mean by that? Well, we're going to do something we've never really seen before, but because of the way we're using the notation, it actually is going to allow us to do something pretty cool. So I'm going to multiply both sides by this dx, essentially moving it to the other side, and we're left with dy equals y times dx. Similarly, I'm going to get this y off this side by dividing both sides by y. And I end up with, I'm going to write it this way, 1 over y dy equals dx. I have now accomplished my goal of getting the y's on the left, x's on the right. This is called separation of variables. Separation of variables. Often it will be 0.1 on one of these FRQs. So you'll see an FRQ in the discussion. The first part is creating a linear approximation using a tangent line. Second part is over or under based on the second derivative. And the third part is this process called finding the particular solution. And the first point would have been, did you get the y's on the left and the x's on the right? Now comes the calculus side of things. We're going to integrate or find the antiderivative of each side with respect to its variable. So notice our old notation is back. This side is saying take the antiderivative of y with respect to y. So we do that by taking the antiderivative. So now we're back into, do you remember how to take antiderivatives by hand? So we get to review this again. Antiderivative of 1 over y is natural log of y. Technically, yes, it should be an absolute value. So anytime you take an antiderivative here, don't forget that you need absolute values. It's a domain thing. Now, what the heck's going on this side? Oh, actually, and technically, yes, we took an antiderivative. So plus c, because it's an indefinite integral, equals. Take the antiderivative of this side with respect to x. Well, since there's really nothing there, there is something there. It's a 1. What is the antiderivative of 1? It's x plus c. Cool. Now, if you notice, we have c's on both sides. Are those the same c? No. Those are not the same. So often, don't label them both c. Sometimes we'll do this, label one as c1 and c2. Or a better situation is, just think about it like, at this point, you could move this variable to the other one. So like, for example, if this had been a 2 and this had been a 7, we could have combined them together. So we're going to kind of combine them together into one constant value. We can still say it's an unknown constant, but really the shortcut I'm trying to get at is you don't need to have a c on both sides. Just have a c on one side. It's showing that, yes, there's a constant somewhere. It could have been on both sides, but we're going to combine it all together now into just one c term. So you may want to make a note to yourself if that's something that's going to confuse you, that we just have the c on the x side typically. Okay, so now we're at a point where we can't really do anything else, except what we could do is we can find something called the general solution. So we can find the general solution. How do we do that? Isolate y. So how do I isolate y? I have to get the natural log off this side. How do you undo a natural log? Well, we've seen it a couple times, and it's going to come up again. You would need to raise each side as a power with e as the base. That cancels. Yes, it's absolute value of y, and we'll deal more with that later, how we kind of deal with that. But the general solution would look something like this. And if we're dealing with positive values of x, this is going to be positive. So for now, kind of fudging over some of the details, but you can ignore the absolute values. And this is one possible general solution. Okay, so this is called the general solution. Sometimes you'll see it expressed differently, and we'll practice this in class, and I'll keep bringing this up because this is where students tend to get a little confused. When you're adding exponents, there's an exponent rule that says this. It says if you have x to the 5th plus 3, that's equivalent of x, that's equivalent to x to the 5th times x to the 3. This is an exponent property in reverse. So if we're multiplying two exponents with the same base, we add the powers. Same thing, if we're having two powers added, we can split it apart. So sometimes you'll see this represented this way, e to the x times e to the c. And then if we have this e to the c is just some constant, because e is a constant and then c is a constant. So oftentimes you'll see it represented this way. They'll just recategorize this and they'll just call this big C times e to the x. That's fine too. Okay, so all of these are just what I would call a general solution because we don't know anything about the initial condition. If I don't give you any information about the initial condition, we just say that it's the general solution. But let's back up, back to this point right here, when we got here. So I'm going to rewrite this. When we got here, right after the integration part, most of the time, they're going to give you an initial condition. So if the initial condition is, and let's say, for example, I gave you, it has to go through the point f of 3 equals 1. Well, now what you can do is you can plug in the initial condition. So at this point, before you isolate, plug in. I would plug in now. It's easier to solve for the C value if you plug in the initial condition before you get y by itself. So yes, you can still get y by itself and then plug in the initial condition and do it that way. But I think it's way easier to, once you do the integration, plug in the initial condition. So natural log of, and this is where the absolute value goes. If I plug in 1, 1's absolute value is still just 1. X is 3 plus c. What is the natural log of 1? It's going to pop up a lot, so you need to know that it's 0. So c equals -3. Now plug that, and remember this little c is not the same as this big C over here, so don't try to do weird stuff and combine the two. This is a separate way of doing the problem. Combine this, or sorry, plug this in here. So natural log of y equals x minus 3. And now you can big C, or big C, big E. Boom. And actually this answer is fine. Again, the absolute value, we'll talk more about that later. I'm not super concerned about the absolute value stuff right now. So if you're confused about the notation, we'll build that later. Right now, I want you to be able to get through this process. This answer is fine. Or in reality, you could have kept going and said, okay, this is e to the x times e to the -3. And negative exponents go to the bottom. So y equals e to the x over e cubed, I guess. But typically this answer, the reason why I like doing it this way is because this answer is the one I would look for typically. So back to this one over here. Had you tried plugging the initial condition in at this point, you would have gotten 1 equals c e to the 3. You would have divided by e to the 3 and you would have got the same answer. So you would get big C equals 1 over e cubed. And then plug that in right here. And it's the exact same answer. Okay. I still think it's easier to go through the process, plug in the initial condition first, then isolate y. That's how one of these problems goes. So let's do 2 more so you can, again, watch the process. All right, so this time let's do a little bit more tricky one. So dy dx equals 2x y to the 4th. All right, and we're going to find the particular solution. So find particular solution with the initial condition. Let's do f of 1 equals 1. Sure, keep these small. All right, so we go through the process. Anything that's got a y, typically you're going to divide the y's over. Sometimes if they're in the denominator, you're going to multiply them over. So I'm going to divide over the y to the 4th, but I like to put it as a denominator. And I'm going to multiply over the dx. Notice I kept the 2 on this side. I think it's way better to keep coefficients on this side always. You could have divided the 2 over with the y to the 4th, and you still would have got the right answer, but it's way more common that you're going to make mistakes if you do that. So keep coefficients on the x side. All right, now we're ready to integrate both sides with respect to its variable. So this is where it's not a natural log. Common mistake right here is to tell me that the answer is natural log of y to the 4th. No, this is a reverse power rule. Write this as y to the negative 4, and then go backwards. Add 1 to the power, so y to the negative 3, and then you got to put a negative 1/3 in front so things cancel. Okay, so don't forget your integration rules here. We don't need a c on this side because we're going to put it on the other side. Antiderivative of 2x is x squared plus c. Now, you could get y by itself here. I would not. I would, like I said earlier, use the initial condition now. So let's plug this initial condition in and solve for c. So negative 1/3 1 to the negative 3 equals 1 plus c. 1 to the negative 1/3, well, 1 to any power is 1. So negative 1/3 equals 1 plus c. Minus the 1 over, we end up with a negative 4/3. So there's my c value. Plug that back in here. So we end up with negative 1/3 y to the negative 3rd equals x squared minus 4/3. Okay, calculus is over. You just need to get y by itself. How you do that depends on how good you are at maneuvering equations around. But typically you'd get 4 out of the 5 points for this. The last point is, can you get y by itself so that you find the actual particular solution? So here's my advice. As soon as you see fractions like this, I would get rid of the fractions by multiplying both sides by 3. It works nicely in this case. So you'll end up with a negative y to the negative 3 equals 3x squared minus 4. Cool. Next, I see a negative here. I'm going to immediately fix that by flipping the signs of everything. So y to the negative 3 equals negative 3x squared plus 4. Now, how on earth do I get this y to get this negative 3 exponent off of it? Well, I'm going to rewrite this as 1 over y cubed equals negative 3x squared plus 4. I'm going to put this over 1. Why? Because you're allowed in math, if you have 2 fractions that are equal, you can flip both fractions. That's going to allow us to get y out of the denominator. It's almost like cross multiplying and then dividing. It's a shortcut. So you end up with y cubed equals negative 3x squared, 1 over negative 3x squared plus 4. And then the last step is to cube root both sides. y equals cube root of 1 over negative 3x squared plus 4. Technically, you could split the cube root to the top and bottom and write it as 1 over cube root of and so on, but that's fine. This answer is totally fine. Once y is by itself, you've accomplished your goal. And that is the particular solution. This solution is the original function with this slope that goes through this point. Okay. I go about this very nonchalantly because I've done it a million times. This is not easy. People make mistakes all the time. So if you're like, dang, I made a mistake, I'm bad at this. No, it's pretty common to make mistakes. So we'll practice this a lot. All right, let's do one more though. One more. Same idea. Let's just see another case of a differential equation. How about x over 5y? I'm just trying to give you a couple different cases of where variables could be. So in this case, if you notice, the y is in the denominator this time. So let's multiply it over to the other side. And now I said in the last one, keep coefficients on the side with the x. So I'm going to multiply both sides by y, move the dx to the other side, but keep it as 1/5 x dx. Even though that looks a little gross, it's going to be better in the long run. Trust me. Now we're ready to integrate both sides with respect to its variable. So the antiderivative of y is 1/2 y squared. Antiderivative of x is x squared with a 1/2 and the 1/5 that's already there, so 1/10 plus c. And I didn't give you an initial condition, so let's say the initial condition is f of 10, why not, equals 4. Make it easier on ourselves, yeah. So if f of 10 equals 4, let's plug them in. So 1/2 4 squared equals 1/10 10 squared plus c. 4 squared is 16 divided by 2 is 8. 10 squared is 100 divided by 10 is 10. So c equals -2. Plug that back in here. And we end up with 1/2 y squared equals 1/10 x squared minus 2. Cool, so close. We just need to get y by itself. Well, to get rid of 1/2, we can multiply both sides by 2. We would have y squared equals 1/5 or 2/10 x squared minus 4. And then we square root both sides. And we have found our particular solution. That's it. So we're actually finding the real function. This function, if you check it, has this slope all along the way. So I think what you can actually do in Desmos, real fast, just to give you a way to check this, if I graph this function, x squared minus 4. Let's call this f of x. And then I say g of, sorry, stay with me for 1 sec. Getting this set up. Okay. And then, I don't know if this actually works. I think it does. I don't use Desmos for this type of thing before, but let's find out. Did it work? Ah, it did. Okay, this is pretty cool. This is pretty slick. So check this out. This is what I did. Okay, graphed our answer. This is the answer we got. 1/5 x squared minus 4. Said, okay, find its derivative. We could actually go back now and find the derivative the real way, because look, the original function has no y in it. And then look, I can check that the differential equation matches with the derivative by taking the differential equation, which was x over 5y, and y just means the original function. Y is the output. It's the original function that I don't know. So in place, if y equals this, I plugged this into the place for y, and look what happens. Same answer. So yes, you can plug the particular solution into your derivative, and that answer should equal the derivative of that function like you weren't taking it with respect to y. Now, that's a little weird. But at the end of the day, remember, this differential equation is in terms of x and y. And what this y really means is the actual function itself. Just like when we had dy over dx equaled y, that y was equivalent to e to the x. I know that's a little confusing, but this is a cool way to check. So go back and watch it again if you're a little confused on why this works. It is a nice way to see that your particular solution actually does work. But really, at the end of the day, we're just finding antiderivatives and solving for c and then getting y by itself. All right, that's it.